Hello. So the second part of this week 3 thermodynamics PowerPoint is all about these energy diagrams. The first half is just the 3 laws of thermodynamics. So energy can't be created or destroyed. The second law is entropy. And then the third law is that at absolute zero, there is no entropy. And that stuff's pretty much just, kind of more definition based. But the energy diagrams are about actually reading a graph, and that can get kind of tricky, especially when you're just trying to see it on your own. So I wanted to record this just to kind of go through the second half of the lecture so you guys could hopefully get a better understanding of it. So the idea behind an energy diagram is what we're looking at here. This graph is showing us a picture of a before and after during a reaction, right? So it says reaction down here at the bottom, and it's because this is time, right? So reactions are a reaction is happening. So hydrogen gas and oxygen gas combining to form water, or sodium and chlorine combining to form sodium chloride. So we have some reactants on the left side and some products on the right side. So think about the like balancing equations. We have the left side of our reactants, we have the right side of our products. And that's what this graph is pretty much showing us. First thing that we wanted to say is that the units for this are for heat are in joules or kilojoules. If we're looking at like a kilojoule is 1,000 joules. And that is our energy here, and it's potential energy, which is stored in the chemical bonds of the substances and the whole thing. And we learned about joules a little bit when we did last week when we looked at the Q equals MC delta T equation. That Q, the heat value, is in joules. And so it's the same idea here, is that there's some energy that's stored in these bonds in the reactants and in the products. And this graph, this energy diagram, tells us the energy stored in the reactants, the energy stored in the products, and kind of what happens in between there. So at the beginning of the reaction, there are reactants with a certain energy, and there are products with a certain energy. So we see here that this line right here, this line here represents our reactant level of energy, and this line over here represents our product level of energy. So each line tells us how much energy is stored in those bonds between our reactants and between our products. And they can be either way. We could have the reactants higher than the products, and we could have the products higher than the reactants, and that determines the type of reaction. But either way, it's all about that we have some energy stored in our reactants and some energy stored in our products. So in order for the reaction to actually start, there has to be something called an activation energy. That energy is how much has to be put into the system in order to actually make the reaction happen. So back to like hydrogen gas and oxygen gas. Hydrogen and oxygen gas are in the air around you all the time, but they are not constantly combining to form water because they don't have the proper activation energy. They're not being combined in a way that is reaching that threshold, that activation energy threshold, that then leads to a reaction to create products. So they just stay in their reactant phase. We have to apply some energy into the system in order to force hydrogen and oxygen gas to combine into water. It happens under very specific circumstances. It's not just happening all around you all the time, because then we would just be covered in water all the time. So that's what this activation energy here is. It goes from the reactants all the way up to the top of the peak here. Okay, so we go from reactants to the top of the peak. And again, the reactants could be down here, and the peak could be at the same part. It could take way more activation energy. There's also situations where it takes basically no activation energy, where there's reactions that happen spontaneously, or they happen without you really needing to do anything. And those are just require way less activation energy. So this EA is the minimum amount of energy to start a reaction, that activation energy. So it's EA is the energy of activation. And yeah, so that's just how much energy it takes to actually get a reaction going, and that's represented by the little camel's hump here, this little peak in the graph. Okay, so the end of the reactions are where the products, so at the end of the reaction, there are products with a certain energy. So we said at the beginning there's reactants with a certain energy. At the end, there are products with a certain energy. And what we call the heat of reaction, the difference between our reactants and our products. That's how much heat was put off by or retained by the reaction. Is this heat of reaction the difference between our reactants and the difference between our products? So whatever value this is, subtracted by each other, and we end up with this heat of reaction. So delta H is the difference in energy of products and reactants, and that is that products minus reactants. So we always do final minus initial. It's a delta H, so it's a change, and we always do final minus initial whenever we look at a change in something. And this delta H is the change in enthalpy, or the change in energy between our products and our reactants. And so we would do our products minus our reactants. And so we would have 50 for our products minus that 20 for our reactants. 50 minus 20 would give us a delta H of 30. Delta H is positive, and the reaction is endothermic. And from before, we remember endothermic is a change in energy that results in the substance retaining the energy, making the surrounding colder. So the product pulled energy in. It needed that energy to do whatever it did to raise its energy level, its personal energy level, which cools the surroundings. If that delta H is negative, then the reaction's exothermic. The surroundings got hotter. It released the energy into the surroundings, making the area around it hotter. That's your flames, your explosions, stuff like that, making the energy or the surrounding hotter. And that would be if the products and the reactants were flipped here. So if we had the reactants at 50 and the products at 20, we would have a delta H of negative 30, telling us that our reaction was exothermic. We lost some energy. Okay? And notice how in this case, when we're doing this delta H, the activation energy doesn't come into play. That's just how much energy we need to get the reaction going, but it has nothing to do with our change in our delta H. Okay, the delta H is just the products minus the reactants. So a couple different graphs here. We have an exothermic graph, where if we did the products minus the reactants here, this minus this would be a negative number. And so we would end up with a negative delta H, which is an exothermic reaction. And notice that exothermic reactions are going to tend to have a little bit lower activation energy potentially, whereas endothermic reactions will see this a little bit higher skew here, right? Because we have to get up over our energy of our products in order for the energy or for the reaction to start. Whereas here we're already above our energy of our products, so we just need whatever energy put in order to get it to activate. And then endothermic here, we have a higher energy of products, so higher energy of products minus the lower energy of the reactants, and we end up with a positive number. And if we go back, that positive delta H is endothermic, and that negative delta H is exothermic. And so this is an example of an exothermic graph, and the reactants could, go higher, the products could go lower, they could go closer together, but as long as the product energy is less than the reactant energy, it's exothermic. And as long as the product energy is greater than the reactant energy, it's endothermic. So this could be way higher, and this could be way lower. There could be a huge activation energy, or there could be a much smaller activation energy. These could only be off by 1 joule or kilojoule of heat, and it would still be endothermic because some energy was absorbed. So just the quick examples here. So does this require a little bit of energy or a lot of energy to start, as in our activation energy? Does this require a little bit of energy for activation or a lot? So we start at 50. We start at 50 and we go all the way up to 250. Sorry, my headphones told me that they were about to shut down, so I got distracted and had to stop that from happening. We go from 50, we go up to 250. Okay, so we went up by 200. Whereas our energy between our products and our reactants is 50. There's only a 50 difference. So that's a lot of energy in order to get this reaction to start. That has a very high activation energy. Is this reaction exothermic or endothermic? Well, we have a higher product energy than we had reaction energy, right? So we ended with more than we started with. So that means that we're going to have an endothermic reaction. The energy was put into the products, which energy was pulled in from the surroundings, would have made the surroundings colder in order to change the energy level of our products. So does this reaction have a positive or negative delta H? It's an endothermic reaction. Endothermic reactions have positive delta H's. Okay. And more specifically, if we were actually to figure out the delta H, it'd be 100 minus 50, final minus initial, and we'd have a negative or a positive 50 delta H. And then the last example here, what is the activation energy? It specifically is asking us what is the actual activation energy. And the activation energy, we go from our reactants up to the peak here, okay, the max peak. So we go from 40 up to 100. Oops, 40 up to 100. So the activation energy is 60. Okay, we went from here all the way up to here. So it took 60 kilojoules of energy in order to get this started. And again, it's always a final minus initial. So our final point minus our initial point, 100 minus 40 is 60. What's the delta H? So what is the actual change in our enthalpy? And our change in enthalpy, our delta H, we do products minus reactants. So we have 20 and 40. Okay, so the change is negative 20 because we did our 20 here minus our 40 here. So we went from 40 down to 20, 40 down to 20. So we lost 20, so negative 20. So it's an exothermic or endothermic. Delta H is negative, so it's going to be an exothermic reaction. So hopefully that helps a little bit. You can rewatch this as many times as you need to. Not too crazy, it's just kind of reading a graph, but there's really 3 points you just need to be paying attention to. You have the reactants energy, you have the products energy, and then you have the activation energy, which is between your reactants and your products. But everything else, it's just as long as you know reactants, products, and then activation is between your reactants and your peak here. Okay, so that's it. Hopefully that helps a little bit. Again, sorry, we're not in the classroom. A lot more understandable when we're there, but hopefully you're doing okay. So be sure to go into the discussion board if you need any help. And I still do office hours on Wednesday, Thursdays, and Fridays at 12. So if you ever have any questions, that Zoom meeting is open at those times. So feel free to pop in and ask questions.